Hey everyone! Today, we're diving into a material that has a hidden superpower, a special kind of metal that can actually change its shape on command. I know, it sounds like something straight out of science fiction, but this is a very real technology with some absolutely incredible applications.
So just imagine this for a second. What if you could take a solid piece of metal and just by using a magnetic field, make it stretch out or shrink down? Now, we're not talking about some huge movie-style transformation. We're talking about an incredibly precise, almost microscopic movement. And that tiny shift is the secret behind some of the most advanced tech we have today.
So, this isn't magic, right? It's a really remarkable property that only certain materials have. And of course, it has a scientific name that pretty much perfectly describes what's going on. It's called magnetostriction. Yeah, it sounds a little complex, but the name actually tells you everything you need to know. You've got magneto for the magnetic field, and striction, which basically means to tighten or squeeze. So you're literally using magnetism to make a material constrict or expand. When you boil it all down, the relationship is super simple and direct. You put magnetism in, you get a shape change out. This effect is incredibly reliable, though how much it changes really depends on the specific material we're talking about. You can actually see this effect in common metals like iron and nickel, but the change is just tiny. But then you've got materials like terphenyl D. This stuff is a special alloy, basically designed from the ground up to be a magnetostrictive powerhouse. Its shape change is hundreds of times greater, and that is what unlocks its real potential. Okay, so how on earth does an invisible magnetic field physically change a solid piece of metal? Well, the answer isn't on the surface. To get it, we have to look deep inside, all the way down to the atomic level. So, picture this. The material is just packed with trillions of microscopic magnets called domains. Normally, they're all pointing in completely random directions, kind of canceling each other out. But the moment you apply an external magnetic field, they all instantly snap into alignment. It's this collective, perfectly synchronized reorganization that forces the entire chunk of material to change its overall shape. It's really just a beautiful and elegant principle when you think about it. A simple outside force creates this perfectly synchronized change on the inside, which results in a totally predictable physical change. That's the heart of how this all works. All right, so we've got this amazing material that changes shape. The obvious next question is, what's it good for? Well, its first huge application is all about creating incredibly precise and powerful movements. Now, the technical term for anything that converts energy into motion is an actuator. Think of things like motors or pistons. Well, magnetostrictive materials let us build a totally unique kind of actuator, one that's unbelievably fast and precise. Because this shape-shifting happens almost instantly, these materials are perfect for creating super high-frequency vibrations. This is the exact technology behind those ultrasonic cleaners that use vibrations to blast dirt off of delicate jewelry. It's also used to create the powerful pings for sonar that submarines use to navigate the deep ocean. And that right there is the key. The movement itself might be microscopic, we're talking just a few micrometers, but it's delivered with incredible force and speed. That combination of pinpoint precision and raw power is what makes this stuff so valuable to engineers. But wait, creating movement is only half the story. This amazing effect also works in reverse, which turns these materials into highly sensitive sensors. So let's flip the script. Instead of applying a magnetic field, what happens if you physically squeeze or stretch the material? Well, the exact opposite happens. That physical stress forces all those tiny magnetic domains inside to realign, which in turn changes the material's entire magnetic field. This lets us build sensors that are both incredibly precise and super durable. By measuring the change in the material's magnetic output, we can calculate the exact amount of force, pressure, or even torque being applied to it. You'll find these sensors in everything from massive industrial machines to delicate scientific instruments. So when you put both of these abilities together, the ability to move and the ability to sense, you realize this isn't just one-trick material. It's like it has a two-way superpower. It's a perfect symmetrical relationship. It's a two-way street. For an actuator, you put a magnetic field in and you get movement out. For a sensor, you put physical force in and you get a magnetic signal out. This constant back and forth between the physical and magnetic worlds is what makes these materials so unbelievably versatile. And that is exactly why we call them smart materials. They can both act on their environment and sense changes within it. This dual capability makes them absolutely essential for any system that demands the highest possible degree of precision, reliability, and control. So, when you have a material that can so elegantly convert magnetism into motion and then back again, you just have to wonder, what's next? What amazing future technologies will be unlocked by these incredible shape-shifting materials?